I'm screaming. I'm screaming. Okay. Copy URL. Send it to Yubs.
Better not send it to me.
No? Okay, folks. Another day, another class, another lecture. And today we have homework, don't we? We have to answer a couple questions. The first question, well, let's go with the second one first. Second question was, can you come up with an explanation if you have a series of descriptions? In other words, do a series of descriptions, or you add them or whatever, end up or result in an explanation. And well, I hope someone did the homework, but let me just give you my version of the homework. I did the homework. One person did at least. And the way I look at it is the following. I'm going to use the example I used yesterday. You know, I come home and there's a broken window. Glass is on the floor, right? And so I ask, well, how did the window break? I'm inquiring, I'm requesting a theory, an explanation. And now the question is, you know, can you answer that question with a whole bunch of mathematical, especially, descriptions? And let me give you the example that I've got in my mind. Finish with that, and then I'll turn it over, maybe to my son, who's on the other side of the desk here.
Hi, guys.
And he might want to challenge that, but here it goes. Here's the ET, right? And I'm a guy from Mars, little Martian. I'm going to explain to him how the window broke. So
he's got nothing. You got nothing better to tell an alien.
Yeah. How the window broke.
That's all the guy wants to know.
So I'm going to be as objective as possible, and I go up and I start this way. I said, you know, Johnny's arm has so much energy, 100 ergs or whatever. A rock has so much mass, X mass. And if you move that rock at certain speed, you get X force, newtons or whatever. And you know, glass is very brittle. We could run an experiment and show how brittle it is, how soft it is. You know, all I've done is descriptions. Now, yeah, from all those things, you might intuitively say, well, I think I know what he's trying to say. I think I know what happened. But if we objectively look at just those descriptions, have we explained how the window broke and why the glass is on the floor? That's my point of view. A whole bunch of descriptions do not add up to an explanation. An explanation is how something in physics is how something occurred, the mechanism, what caused it, and not, you know, a bunch of descriptions, whether mathematical or otherwise, you know, about time, about force, about field. That doesn't tell me how something happened. And that's my answer to that question.
I guess it's kind of like when, not the defense attorney, but when a prosecutor, when he lays out a whole bunch of evidence, kind of allowing the jury to make up their own minds. But he lays it out in such a way that it's kind of self-evident, like hint, hint, nudge, nudge. And maybe in that sense, a bunch of descriptions kind of are self-evidently point to an explanation. But no matter how you spin it, yeah, you still have to kind of connect the dots.
And you know why? Because each juror is gonna fill in the blanks in his own way, according to his own intuition and his own, the way he was raised, the way he was educated. So many factors, and everybody's gonna have their own explanation inside his mind if the prosecutor doesn't tell him exactly what his theory is. This guy's going to say, oh, it's X, and the other guy's going to say, oh, it's Y. Oh, I know what he's talking about. He's talking about Z. And everybody's going to come up with a different theory when, it's up to the prosecutor, the presenter of a theory, to tell you exactly what he means. And that's what I'm saying, a description doesn't do. Description just leaves it up kind of to the juror to figure out on his own what the prosecutor's saying.
I was thinking about this while I was walking around today. Something along the lines of, it was more of a question where, when can you use the word describe? Because when you use the word describe, you're essentially asking for an adjective or an adverb. Whenever you use a verb, you're not really describing.
Right.
As far as I know. Like, you can't, in ordinary speech, yeah, you can use words any way you want, but scientifically speaking, I think we have to make a distinction when you say, you can't really say, describe how the getaway car got away.
Okay.
It's more, I don't know if you could, in that sense, you'd have to use more explain, like which direction they went, or how they got away, because there we're talking about verbs, not speed exactly or direction. I want to know what verbs did this individual use to get away from the bank in a getaway car, for example.
Right.
And I think we'd have to, in that sense, use the word explain, but it kind of gets clunky when we're talking about when you have to redefine every word for scientific purposes. It kind of gets clunky, and it becomes this kind of barrier to entry for normal people. When you want to explain something, you kind of always have to stop people and say, look, we have to make a distinction between the word explanation and the word description.
I do that
for scientific purposes, but that's what creates this barrier to entry, where people just kind of stop and say, okay, now you're kind of just nitpicking about things that don't really matter.
Yeah, and I like to make a distinction, and that's why I make it very black and white as much as I possibly can. And I'm saying that description, you can only describe in one instance only objects. You can say the cat is dead. That's a description. Dead would be an adjective, and in this case it's an adverb for the purposes of physics because it involves motion.
Would you say the cat is falling? Is that a description or an explanation?
And again, we have to distinguish between in science. In science, we have to distinguish between adverbs and adjectives. The way I want to qualify these words specifically for science is that adjectives only describe objects, like in a static mode, like the cubic box. Cubic would be just a description of the box, right? On the other hand, if I'm going to talk about motion, I'm saying that you have to narrate. It's not really a description. I like to use the word narrate because now you're telling a little story about what happened, how the lion caught the deer, right? For example. So now you're narrating a little story. You're telling a movie. That's essentially what you're doing.
But I think it's very important to use different words when necessary. For example, you introduce a new word, which is narrate, when we're talking about motion, which is better than saying that the cat falling is a description. In ordinary speech you use the description for anything, but for science, to make a very clear distinction, things in motion, you're narrating something. Things static, if it's red, that's just a description.
Right.
And then explanation is, I guess, if you're trying to answer a question.
Right, and an explanation in that context is, the prosecutor or the presenter, the theorist's version of how something happened, how a phenomenon occurred. And that's what I want to distinguish from description. And it's important to note, and I always emphasize that mathematics is a descriptive language. It can only describe. It has no power to explain anything. The explanation is the personal physical interpretation of the mathematician. But the equation just, if you look at it, it's just a description of motion, what I call a narrative. And again, an equation only gives you one point. That's going to be important, what I'm going to go into next. But the any equation, you put a set of values and it gives you only one result. If you want more results, you want to see a trend, you want to see motion, you have to keep changing the values on a variable to see that motion. Otherwise, for every single set of numbers that you use to replace instead of variables, you only get 1 point. You only get one result. So you get all these locations, and only when you put them together with different numbers, then you see a trend, then you see motion, then you see some kind of movement. But you won't see it with a single equation. So it's important also to distinguish that. Anyways, let's get back now to the first question that was out there for homework. And let me repeat the question. The question, I'll put it up here. Here we had the astronaut. He's falling to Earth. He's being pulled by the Earth, so there's a gravitational acceleration. And so that's what we say, the astronaut has, we refer to that as gravitational mass. On the other hand, if you're in a rocket in the middle of a space, the picture at the bottom, and you're flying at the same speed, 9.8 meters per second square, at the same acceleration, that's going to be your inertial mass. What Einstein said is those two are physically equivalent. And if you look at the picture, you say, well, yeah, they're physically equivalent because I don't see any difference between the guy on the top and the guy on the bottom. Essentially they're the same. And here I show what the difference is. Okay, and we see it in motion. Once we put the ropes that connect every atom of the astronaut, we see that there's a difference between how he falls to Earth, being pulled by a whole bunch of ropes that are effective ropes that are constantly going at different angles as he approaches the Earth, versus the rocket where the guy is simply pushed against his seat when the boosters send the rocket forward. So in the bottom case, in the case of the rocket, there are no ropes involved in the motion, in this acceleration that he has. On top, there is. And so now we have a difference. We have a difference between the top and the bottom. There's a physical difference. That's what I'm saying. They're not exactly the same. In the top one, we have ropes involved, and there's a pull force. In the bottom one, there's a push force, and there are no ropes involved.
But essentially, you're saying that even though the speeds are the same, it's how the speeds are generated.
Correct.
That's not the right word. But
well, yeah, but you're on the right track. What I'm saying is numerically, and with including the units, that's important too. If you look at the number, the absolute value here, just the value that you have there, a 5, a 6, a 7, 7.1, all those numbers and the units, they're exactly the same on the top and on the bottom. And that's why the mathematicians say, oh, it's the same thing physically. But it's not the same thing physically, because there is a qualitative difference between the top scenario and the bottom scenario. And that's what I'm pointing out.
Essentially, we're saying that if you pull me at 9 meters per second, is different than if you push me at 9 meters per second. They have the same
yes
effect.
And no. Yes and no.
They have the same effect, okay. But
there's something else, and that's the ropes.
There's a difference in how you're generating the motion.
Yeah, and again, I'm trying to make the ropes visible to show that the mechanism is also different. One thing is, like he said, if I push you and I pull you at 9.8 meters per second square, essentially you move in the same way, one way or the other. It doesn't really matter to you because you're being pulled or pushed at the same speed. Numerically, it's the same. But now if we look at this as, you being pulled by a bunch of ropes that are tied to every atom in your body, and you're being pulled like you're falling from an airplane and the earth pulls you from every one of those ropes to the center of the earth, that's a little different than saying, well, you're in a seat of a rocket and you're being pushed upwards, in fact, against the ropes, if anything.
Isn't that the same thing as saying if you're shot out of a cannon or if you're pulled by a rubber band, the speed, we're not talking about how fast,
Right, the acceleration.
If you're moved by both at the same exact amount, the same exact force. If the rubber band pulls you at 9 meters per second squared, or if you're shot out of the cannon at 9, I guess you can't do per second squared there, but whatever.
No,
10 meters per second, you can't really get shot per squared out of a cannon. You don't go faster and faster.
Well, let's assume you could for some reason.
That confuses. If
you could, as soon as you're coming out of the cannon, you probably are.
If you're shot out of a cannon at 10 meters per second, or if you're pulled by a rubber band at 10 meters per second, even if the speeds are the same, even if the effects are the same, assuming they are, I mean, I guess
well, for you they are.
From the middle,
for you they are. You're flying one way or the other.
But even if the speeds are the same, it's how you're moved that makes the world of difference, because then if you try to put it in certain situations, like the one I talked about yesterday.
Yeah, about the ball.
The torus, if you throw a ball up.
Then you got to look at the qualitative aspects as well.
Watch yesterday's.
But let me. So we moved on to the next issue, and that was, you got to build a torus for NASA. You're an engineer at NASA. You're going to build a torus, and that torus is a space torus. It's going to be flying in space with 10,000 people, in it, and you're going to create artificial gravity. The torus is going to spin. It's going to create 9.8 meters per second square gravity, or artificial gravity. It's going to be inertial type of gravity, inertial mass. That's what we're talking about here. And I'm going to put it up here, and that's what it is. That's what the torus looks like. It turns, they say, 3 times per minute. And that centrifugal force creates a gravitational acceleration similar to what we have on Earth, 9.8 meters per second square. Calculated, fine, no problem. The question we had yesterday, and that was the homework one, and that's, here we have the torus again in a static mode. We have to assume that it's moving in the direction of the yellow arrows, and that's little u there in the beige color, if you can see it on the right in the center of your screen almost. That's you. You're standing against the edge of the torus, and because the torus spins, you are pushed outwards. As you can see, if the Earth was on the side where the words pull, where the word pull is and the question mark, the red ones, if the Earth was there, it would be pulling on you with threads, with ropes. But here we have nothing in that direction. What you are is being pushed outwards, by the spinning wheel. And so the question, the $1 million question, that's the homework, is there first of all, is there a physical difference? Okay, is there a physical difference? Is this the same thing if you're on Earth just sitting, against the ground, or flying in space with artificial gravity, which is really Newton's second law, inertial gravity? Is that the same? Does it have the same effect on your body? If you lived 20, 30 years, right, in space, would that be the same thing as living those same 20 or 30 years on Earth, where you're constantly being pulled, every atom of your body, by the Earth's gravitational acceleration field, whatever you want to call it? That's the issue.
One difference that I can think off the top of my head is there'd always be a time lag. Like if you stood on your head on Earth, all your atoms are always getting pulled down constantly. There's no lag. But like if you were standing and then you suddenly jumped and did a handstand,
okay,
there'd be no time. Even in the air, you'd still be being pulled. Well, I think here, would there be a time lag? Like if you were on the torus and you were standing where that guy is,
yeah,
you show him, and he just jumped up and did a handstand, would there be a time lag where all his atoms would then go to his head?
The atoms have gone to your head?
the momentum has to catch up. I don't know.
Well, that's again, that's the homework. And what, you didn't do the homework? No problem. I'll give you an extra day, okay? You got one more day to think about
Your
this.
homework too.
Well, yeah, I know. I'm doing my homework. I'm slow.
I wish I could say that to the teacher. I didn't do my homework and I'm still working on it.
Okay, but where does all this come from? Okay, it comes from Mr. Einstein, and he says gravitational mass is the same thing as inertial mass. They're both equivalent. That's his principle of equivalence. Okay, and what is that really? Let's get deeper into this thing. What we're talking about here is Newton's second law, right, of motion. Force equals mass times acceleration. That's your inertial mass there. And we're pitting that against Newton's law of universal gravitation, which is force equals the g, the gravitational constant, mass times mass divided by distance squared. What is the important part of that? It says that mass, an object is far away from another object. The closer they get together, the more the force will increase. The F will go up. And the greater the distance, that distance square at the bottom, the greater the distance between the masses, the smaller the force. In other words, force is inversely proportional to distance and directly proportional to the masses of the two objects. That's what Newton's saying. The question that Einstein investigated was or the one he stated, is that these two equations are one and the same essentially. He's saying that Newton's second law, the inertial mass, is equal to Newton's law of universal gravitation. Why is this important for relativity? It's important for relativity because from this, Einstein evolved or developed the idea that light curves in space. Now, how did he come up with that?
I thought of another example for the torus, by the way. So.
Okay, keep it handy there. Hold on. Here's Einstein's version of how light bends or warps. If you're standing still in an elevator, right, and the elevator is going to go upwards, okay, you're going to be pulled upwards. That means you're going to be going according to Newton's second law. That's force equals mass times acceleration. You're going to be drawn upwards. That means you're not going to be pulled by gravity in this case. Right now, you've got a booster rocket under your elevator, right? And it's going to push you upwards. When you're standing still, you look inside. That's for the viewer. That's for the observer inside the elevator. Light goes, assuming you make a little hole in the elevator and you put a flashlight there and you shine it, you're going to see a straight line. That's what they're saying. If the elevator rises at a constant rate, Einstein says light will curve, will bend sharply and go downwards because it's at a constant rate. On the other hand, if you are accelerated upwards, that means you go faster and faster and faster, light will curve. That's his train of thought. Okay?
What do you mean? Like, if the guy standing there, if in front of him the wall were made of glass and you just had a light, like a laser pointing sideways while it's going up?
Yeah. And
is the laser coming with him?
Well, according to Einstein, light will bend if it's at a constant rate and curve if you're if it's accelerated upwards.
Where is this? I mean, can we call it a laser?
Yeah. You can.
Is the laser attached to the elevator? Is it coming up with him, or is it?
Yeah. It's coming up with him.
Go past the laser?
No. It's going with him.
Okay.
And he's saying that light is bent in one case and curved in another.
So the laser is getting shot, let's say behind the glass.
Yeah.
And if the elevator goes at a constant rate up, the laser's going to be
bent. If it's at a constant rate, bent, and if it's at an acceleration, then it's going to curve. That's what Einstein says. That was his train of thought.
That's a really fast elevator.
Well, because he says that this is what happens with inertial mass, and since inertial mass is the same thing as gravitational mass, he inferred that light curves in space in the presence of mass as well. And that's what he predicted. That was his theory. And we have Mr. Arthur Eddington, And in 1919, Eddington went to the middle of the Pacific. He had, I think, 3 boats, one in Brazil, one in Pacific. He had, I think, 3 boats around the world to look at this eclipse. And he took pictures, and he was able to photograph that picture you see there, that one of the ones he put in his report, his article. And he was able to show that light from a distant star came around the sun, and thus confirming Einstein's prediction and theory that light curves around massive objects. In this case, we have the moon blocking out the sun, and still we can see, you know, the light curving around the sun of a distant star. That's essentially what that is supposed to show. Okay? And so with that confirmation, Einstein became an instant celebrity. His theory was confirmed. So what is the problem with this? Well, let's go back to this little picture once more. Here we have the little man on the right, and he's falling towards Earth, gravitational acceleration. What is it that Einstein missed? Well, I'm saying this is what he missed. He missed the ropes that tie the little man to Earth. This is the way Einstein envisioned it, right? Without the ropes. Here's how I envision it with the ropes. Okay? Let's see if I see it again. Nope, wrong one. Second verse. That one? No. Got that one wrong. Where is it? I lost it.
You had it just now.
Oh. I don't know where it's at now.
The one is weird.
Taurus, no, huh? I lost it. I don't know where it's at now. Second law, and I lost it. It got wiped out.
Whatever.
Okay, whatever. What I was trying to show is, again, that what he misses all the ropes connecting the little man to the Earth. Okay.
I had a question about the bending light one.
And that should be the case because, like Mr. Richard Muller tells us, and he's a professor at Berkeley, says, so, for example, if you have the Earth, there's a big mass here. He draws that little mass, that big mass there, the big M there. And you have you with your little mass here, and that's you standing on top of the Earth there on the blackboard. Every atom on Earth is pulling on every atom of you. Let me repeat that. Every atom on Earth is pulling on every atom of you. You're also pulling on it. So obviously, you know, if every atom is pulling on you, and we're talking about every atom hidden behind every atom hidden behind another atom, they're all pulling on you. Well, how do they pull on you unless we put some kind of entity in there, some invisible entity that something we can't see? You know, we got to make it visible. And that's essentially what we're saying here. We're saying when you got to put something there, especially an elongated object, if you're falling from an airplane, hopefully every atom of you is connected to every atom of the Earth. And by what means, if not some kind of elongated object? And then he adds, the amazing thing about gravity is that it goes right through things. Now, how can you do that? You know, mathematically, you can do it easily. You just put a number. But how do you do that physically? And that's, I guess, the issue, before us. And here we have, you know, the way I usually like to illustrate it. You have two particles, two atoms. Every atom of you is connected to every atom of the Earth. One is the atom of the Earth. The other one is the atom of you. Even if they spin, like I show them there, because they always introduce spin in quantum mechanics, fine. Get them to spin. I don't care. How does a spinning particle pull on another spinning particle from a distance? You got to put something between those two particles. And that's where you have to introduce something elongated, such as the rope, a chain, a cable, you know, a coaxial, whatever you want to put in there, but it better be an elongated something. And it's got to be physical. You can't put mass, you can't put energy, you can't put field in there. And that's where we have a problem. We have a problem because mathematics, again, is not the language of physics. What you need to do physics to explain a phenomenon is introduce objects. You need to make a movie of your theory. Okay? Now, what does Einstein's principle of equivalence say essentially? Well, what it says is that, that weight is this other form is, here it is. Let me put it back up there. The one on the right there, Newton's law of universal gravitation, that's what we use for weight. Weight is equal to, mass times mass divided by distance square. And that's, on Earth, specifically on Earth, that's the formula you would use to calculate weight of someone falling to Earth at different points. In other words, as you get closer to the Earth, you're going to weigh more. If we could measure you with a scale at every point or at every location in which you are at as you fall towards the center of the Earth. So weight is location specific, from the center, always from the center of an object, right? Such as the Earth. And here I have a little picture of that. Here you see two boxes. They're both cubic boxes, cubes, whatever. And they're exactly the same, but they weigh differently depending on their location near the center of the Earth. The one on the left here is going to weigh more than the one on the right. If you had a scale, you could weigh it at that point in time. And the concept is known as a gravitational field. And I try to draw there the gravitational field, what they have in mind, what the mathematicians have in mind. What you have is the red circle, and that's closer to the Earth, and the gravitation or gravity at that point is a little stronger than the orange one, which is stronger than the yellow one. And as you get farther and farther away, the field kind of gets thinner and thinner, it gets weaker, right? And so what I'm showing here, that that's the concept that mathematics has of the field. The field is simply all these little bees that buzz around the Earth, and the stronger bees are closer to the surface of the Earth, and the weaker bees are farther away. And so if an astronaut were to fall, or a box in this case, were to approach the Earth, it would weigh more and more and more as it reaches, first the surface, and then, if it could go to the center of the Earth, it would weigh ever more as it goes inwards. And again, weight is that Newton's law of universal gravitation. What Einstein is saying here, and let me remove it so that we can see, what Einstein is saying is that the second law of motion is equal to that. And the question, that's his principle of equivalence. And the question is whether that statement is true, whether we can do this. And here's the food for thought that I'm going to leave also for tomorrow for those who want to tackle the homework. Okay, and here it is, and I'll go through that in a second if you give me enough time here. The difference is distance. Okay, and what no mathematician, from Newton to Hawking, passing through the greatest mathematicians on earth, such as Maxwell and maybe Einstein and so on, none of these people realized the qualitative difference between Newton's first law, and let me pull it down a little bit, and Newton's second law. Okay, Newton's universal law is weight, and it's a gravitational mass. The first one is equation of motion. It's a dynamic equation. And what I'm saying is that acceleration in the Newton's second law does not equate to anything on the right. Okay, the one on the right is a static distance. It's a separation between the two masses, whereas the first one is an acceleration away from a starting point, from another mass, you could say. Okay, and here I've put it in a little chart, and you can see the differences. Let's see if I can read this. It's kind of little. Let's see if I can make it bigger for myself. And it goes like this. The gravitational mass on the left is the distance is different than the distance traveled in Newton's second law. Distance traveled means that an object travels away from another object, whereas distance, the physical distance, the one of physics, which is the first one, gravitational mass, is simply the separation between two objects. So those two are a little different. And these people never noticed the qualitative difference between the the little d, or the distances involved in gravitational mass versus the distance involved in the force law, in Newton's second law. And here it is. In one case, distance is static. In the other one, distance is dynamic. In the first one, distance is between two objects. In the second one, distance is traveled by one object. Okay, you have force equals mass times acceleration. The mass is accelerating. You're looking at motion. In the other one, you're having mass versus mass. You're just looking at the distance that separates the two. Okay, so if you just look at one point in either one of those equations, in one case you're talking about the acceleration at that point in that location or at that point in time. Whereas in the gravitational law, what you see is simply two objects separated by distance.
But hold on, with 0.2 of inertial mass, distance is traveled by one object.
In the second law, or what? Yeah. Oh, in the inertial, yeah, in the second law.
Distance is traveled by one object with respect to another.
Yeah, or to respect to, or with respect to its starting point, you can say, because it could start at point. It's a rocket, and suddenly you turn on the boosters and you say, well, what was the acceleration from that point? So you really are equating it to, or your starting point is where the rocket started. At the moment you're taking the initial location of that rocket as the starting object, as the object from which you're escaping. You know, that's what you're doing.
So it's not exactly distances traveled by one object.
Well, it's distance traveled by one object because it's comparing against itself, in the sense that here's where the rocket was before, now it's over here, right? What I'm saying, it's different than saying that the distance is between two objects, two distinct objects, the moon and the earth, for example. That's what I'm saying. And then number 3, each frame in the movie depicts a static distance, again, whereas in the other one, each frame in the movie is a cross-section of an itinerary of one object. Number 4, distance decreases when acceleration increases. In other words, if the objects are accelerating, in other words, if you get them closer together, the distance decreases. On the other hand, in the other one, acceleration is going to increase because acceleration is going to go away from its starting point.
Distance is going to increase.
Distance is going to increase. Number 5, distance is towards the other object. In other words, the objects are coming together. The closer they are together, the stronger the force. Here, the distance travels away from an unspecified object. The faster it goes, the more force it has. So it's the other way around. Distance is a measure of weight, and in the other one, distance is a measure of velocity. And as number 7, force increases when distance decreases, whereas in the inertial mass, force increases when distance increases. So there are qualitative differences, and again, let me pull this out for a second here so that we can see it. Okay, there are qualitative differences between those two equations. They are not exactly the same from a mathematical point of view, but what I'm saying here is that if you interpret that the distance in the inertial mass is distance traveled, and in the distance in the gravitational mass is separation, physical separation, those two distances are not the same. And why have the mathematicians not seen something like this? Well, it's very easy to see. The mathematicians are only concerned with numbers, with meters per second, or things of that nature. They're only concerned with numbers. And you say, well, what is the distance between the two tables? And what he does is pulls out his measuring tape and he starts measuring. And you say, well, what did you measure? Did you measure the length of space between them? That's what he did, essentially. Did he measure the unrolling of the point of his tape? Is he looking at the speed at which his tape is moving across the room and then dividing that by time?
Did he?
Did
he count the air molecules between the tables?
That's well. The way I illustrate that is, let's assume you could put tiles, 1 meter tiles between the two tables, right? And he says, well, there are 10 tiles. So all he has to do, he's already got this standard called a meter. Each tile is 1 meter. He says, oh, there are 10 meters. The distance between these, what is he saying? He's saying, you know, I was able to place 10 tiles, one right after another, between these two tables. So again, he gives you the answer in terms of meters or of tiles, number of tiles, whatever he uses, it doesn't matter. But to him, putting tiles, unrolling a tape, looking at distance and looking at length and looking at distance traveled, they're all the same, because all he needs is the number followed by the unit. And that's where he forgets about the qualitative differences that he never saw. And here you see the qualitative difference. That acceleration there is the distance involved in that acceleration is not the same distance as the distance in the universal gravitation law. In the universal gravitation law, what you have is separation. In the other one, you have distance traveled. And that's essentially the difference. And so not only do we have this physical difference, but then, like I showed in the other pictures, what you have is, you know, this, where is it? Let's see if I can find it without losing it this time. Let me make this smaller so I can find it. And what we have is the dynamic principle of, you know, you have this guy falling. And again, that's different physically than the guy on the bottom who is an inertial frame. That guy's inertial frame is with respect to the seat of his ship, whereas the other one, he's being pulled by ropes. One is a push and the other one's a pull. So there's also a physical difference there. So yes, the principle of equivalence of Einstein is not true. It's not. It's irrational, and it's irrational because they never factored in qualitative, you know, factors.
Just to clarify,
yeah,
the question I had earlier with the light, is Einstein saying that if you put a flashlight on a car sideways, so it's shooting out perpendicular to in respect to the direction the car is moving,
the light will bend.
It's spraying like it's falling behind, kind of like a lag. So it's not like lasering through.
Yeah,
it's
yeah.
kind of like
I know what you're trying to get to, because it's counterintuitive, isn't it, what he said? He's saying essentially light bends. So how did he justify it?
Speed.
Yeah, and according to gravity, because he wanted to show that gravity bends light. That's what his bottom line was.
But he is equating gravity with motion at all. Yeah.
He's saying gravity is an acceleration. Gravity is a kind of acceleration, and for him, that type of acceleration is the same thing as the inertial acceleration, which is when a booster rocket just pushes you up at the same speed. Right. So whether you fall to Earth at 9.8 meters per second square or are pushed by your rocket at 9.8 meters per second square, he's saying it's the same.
Isn't he essentially saying that gravity and any kind of motion affects the bending of light?
Yeah, he's saying it does.
So
relativity, special
relativity. Have the headlights of the car on and it's going forward. Is he saying is that why? Was that his justification for light always going at the same speed?
I'm not sure if he used that same reasoning there. I can't remember now. I'd have to look at that.
It stands to reason that if light bends perpendicular, why wouldn't it slow down if it's going forward?
You would think that...
he would have explained the constant speed of light that way, because if you go forward, you're essentially it's bending backwards.
So you're squashing it.
Yeah.
But I'm not sure what he used the same reasoning there. But for the bending of light in space, in a cosmic scenario, he did use the principle of equivalence. That's how he founded it. He based it on this principle of equivalence. He said light, he predicted, he said light should bend around objects in space. We should see it there because massive objects such as the sun, way down the canvas of space-time, makes it curved, and light has no other choice. The little photon has no other choice than to roll around or warp around, this curved space.
Well, you still have to.
That's his explanation. That's his physical interpretation.
You still haven't explained how was the magic trick done with taking a photograph of a star behind the sun.
Well, I wasn't going to show it here because
bending of the canvas of space, then how did he take that picture? Or did he cheat somehow?
Well, I do it with straight lines. I do it with ropes, and that wasn't part of my talk today, because I'm concerned more about the mass part, not about, you know, how light bends. I'm just using light bending as an example of the fact that Einstein, because he used the principle of equivalence, right, to infer that light should bend in space, when Arthur Eddington confirmed that with his picture in 1919, you know, Einstein became a celebrity overnight because he had predicted that that's what would happen. And they said, well, is that true? And these guys went out into the ocean, they took pictures, and they said, well, yeah, it is true, you know, so light does bend. And I do have a different explanation, and I don't have the pictures for it because the picture's worth 1,000 words in this case. But just think of it this way. Every atom in the far distant star is connected to every atom in the corona of the sun. And they're all connected in straight lines. In other words, all these ropes are tight. They're taut. They're stretched to the limit. Okay? So they're all taut. So there's a straight line from, or straight rope, from an atom in the distant star to the atom in the corona of the sun. And likewise, there is a rope, taut rope, from the atom in the corona of the sun to your eye. So all that the star in the far distant, that is far away, has to do is torque the signal to the atom of the corona of the sun, which now relays that pumping through the rope that's connected to your eye. So we can do this all with straight lines. We don't need curved space. But again, you know, a picture's worth 1,000 words. I can put a picture of that, and some of you have seen it. You don't need to curve light. You know, only when you have too many beers does light begin to curve and pink elephants begin to appear. Otherwise, no, you don't need it. And so again, all I'm trying to say is that, you know, the principle of equivalence is untrue. It's not correct from a physical point of view because of the ropes, and from a physical interpretation of the word distance, of what distance is in each one of these two equations. In Newton's law, it's distance traveled. Second law, is distance traveled. And in the gravitational law, the universal law, it's the separation between objects. Okay, and so that's it. That's that's what I have as far as gravitational principle of equivalence.
Oh, I got more to add.
Yeah,
if
okay.
you're in a car or let's say a motorbike,
yeah.
If you're on a motorbike and you're driving on a road, do you weigh less?
You should not weigh less in this sense. Remember, let's assume that you're going in a curved. First of all, let's assume that you're on a planet that's completely round, perfectly spherical, and it's uniformly made. In other words, every atom, let's assume it's all made completely out of iron, so every atom is just uniform. It's a perfect sphere in every sense imaginable. Now let's go with a motorcycle guy. So he's going around in curves. He's always at the same distance from the center of that object. We'll call it the iron Earth. The Earth is made completely out of iron, and it's completely smooth, perfect sphere. Okay. Now this guy's going around, right? He's going around the entire Earth.
Yeah.
Okay. It's a small Earth. He can do it in a day or whatever. Okay. So he's going around the Earth. He's always at the same distance from the sun. So now the question is, if the motion, the fact that he's moving perpendicular to the surface of this object, of this iron object, does that affect his weight? If we could weigh him at every point somehow, you know, we have a scale, just go with him at every point,
he's driving on
or he goes faster or slower, would that change the value on the scale? And again, the horizontal axis should not change the vertical, you know, pull of every atom that's pulling on his bike and on him. It should not.
But there's centrifugal force.
Yeah, okay, but that's again, the centrifugal force is Newton's second law. I'm talking about gravity first. Let's go let's go slowly. Let's go one step at a time. Gravity. Let's look at just gravity. Let's assume this object doesn't rotate. Okay, so
Yeah.
so we're just have a static object in the middle of nowhere, right? And the guy's just going around it.
Yeah.
Okay, so if his motion is the only motion in the universe, right? This guy's going around the ball, this iron ball. He's always at the same distance from the center of this uniform ball. And so gravity should be the same irrespective of his speed. Does it mean if he goes slower that the number of ropes connecting him to the center of that object are going to change? If he goes faster, will they change? No, of course not. Even if he stands still, they're going to be the same. So that's not going to change. Now the second question is, now we have this object rotating. Now we have this centrifugal force.
No?
Oh, okay.
He is rotating.
He is, okay, hold it. Then
He's going around
rephrase
the
the question. Huh?
He's going around the planet.
Yeah, and? No, I thought you were saying the planet was spinning.
Just same
Okay.
still planet.
Okay, and
He's driving.
okay, he's
That
right.
is centrifugal force. Because he's going...
Oh, that's what you're saying. The fact that because he, yeah.
I mean, to take it to the extreme, if he goes at a certain speed, he leaves orbit.
Yeah, Newton's force law going around.
Yeah. The question is, if you're riding on a motorcycle, do you weigh less? If you're still on the motorcycle,
If we're gonna
driving on the
if we're gonna factor that you come apart from the Earth, right? Let's go at a real fast speed, so much speed that you really get off the ground, and start flying. Well, obviously, at that point, you're not, first of all, at the same distance from the center of the Earth, okay? So if you, in an extreme scenario where you really start jumping far away from the surface, then obviously you're not going to weigh the same. Now let's go in between there. Let's say you still have the wheels on top of, still touching the surface. I don't know. We would have to look at if that perpendicular motion has an effect on Newton's second law. In other words, if that, in that case, Newton's second law somehow modifies Newton's gravitational law.
Well, it can save you the effort. They do that with rockets.
I know what you're saying. With rockets, they do it. With rockets, they do it. But the question is, I don't know. I'd have to look at that. I would think that it does somehow affect it. In other words, maybe it's not. But again, in this case, we're not really talking about gravitation, but we're talking about superimposing upon gravitation the fact that he's standing still, anywhere on the. In one case, he's standing still anywhere around the Earth. It's always the same.
This is going back to the inertial mass.
Yeah, but and I would think that
this question was all just to point out what I realized about the torus.
Yeah.
Because if you do the same thing on a torus, if you drive in the direction that the torus is spinning, you get heavier. While if you drive in the opposite direction, you get lighter.
Yeah, because the torus is spinning in one direction, you're saying, and the guy's going in the opposite direction. So
if he goes in the same
so
direction,
he's going to fall towards the center of the torus.
Yeah, or he'll just
he's not going to be squashed against the wall. In other words,
it's a big difference because depending on the direction I guess it's the same thing on Earth. If you drive against the rotation of Earth, and if you drive with the rotation of Earth, I guess you would also gain or lose weight.
Kind of like the airplanes when they travel in one direction versus the other. There's differences, maybe of resistance or whatever.
But these are little minor things that kind of come up when you're thinking about these things.
Yeah.
That might be a difference between the effects of inertial mass and gravitational mass on the torus, for example, because everything's smaller scale, so things you do have bigger effects.
Yeah, and again, what I'm trying to say here is that the bottom line, I guess, is that the principle of equivalence is not equivalent. They're not equivalent physically. Again, physically. I would say even mathematically in the sense only in the sense that one is distance traveled and the other one is distance separation. And separation is not the same thing as distance traveled. But tell that to a mathematician. All he cares about is the numbers and the units. And if the numbers and the units match, he can call it distance, length, distance traveled. It doesn't matter to him. It's all distance to him. And that's, I think, part of the problem, the fact that they do not look at some of these qualitative differences.
Does the distance from the center of the torus change your weight?
Distance from the center of... well, again, that's a good question. You know why? Because, again, how many ropes are pulling you from the center of the torus? Is it uniform? You know, I mean, if we're just looking at weight, weight is a function of how many ropes are pulling you towards the center of an object. For example, you being pulled to the center of the earth. How many effective ropes are pulling on each one of your atoms? And if you're farther away or closer away from the center of those atoms, which you could say is the center of the torus, yeah, you probably weigh differently if you're closer to the. Let's put the torus here. If you're closer, where is it? See if I can find it. Here it is, I think. If you're closer to the inside rim of the wheel, right, versus being squashed against the edge of the wheel, you know, would there be a difference? I would think it is, because now you're closer to the center where most of the atoms are, even though the torus is very light as far as the number of atoms that compose its center. This is not, you know, like the Earth, which is a globe, and except for flat earthers, and no matter where you go on the Earth, you're more or less pulled towards the center of the Earth, approximately at the same with the same gravitational acceleration. Here, the center of the torus is negligible as far as gravitational acceleration. But if you're going to measure your weight in terms of the gravitational acceleration towards the center of the torus, so little matter, yes, I guess the closer you come to the center, the more you weigh. But your weight is going to be very, very tiny, because there is no mass to pull on you. You don't have all these gazillions of atoms pulling on you. You have maybe 1 million atoms in comparison to the Earth. If the Earth has 1 trillion atoms, this would only have 1 billion atoms. So the differences would be tremendous. No, your weight would be in the opposite direction. You would have to put the scale under the little man's feet there, not on his head. Because if you put it on his head, you're not going to get much weight. Yeah, the weight is going to be very, and again, it shows the difference between Newton's second law and his gravitational law, and between, you know, inertial and gravitational mass. They're not the same.
More discrepancies between the two with the torus, because I like the torus because it clearly sets the parameters.
It separates the two. It really it allows you to see.
It isolates the inertial mass essentially.
More so, you know what I like about it, that if you have to build it for NASA, what would you do? Would you, now that you know about the ropes, would you say, oh, let's just build it, because if we turn it around, we're going to get our 9.8 meters per second square and we're done. And here it shows you that physically they're different. And the question is, you know, is this going to work in the same way as you on Earth? And I'm saying it doesn't.
I think it does.
Well, again,
for all practical purposes.
Does it? I don't know.
The only difference would be, again, if you're driving, which direction you're driving might change something. Because if you drive too fast, you know, I think at least.
Yeah, but is it the question is it the same effect, physical effect on your body, that every atom of your body is pulled to the center of the Earth, as in this case, where we're not talking about the ropes, you're just being pushed towards the edge of the wheel that's turning, right? Even if you go in the same direction and all that stuff, right? Or you stay in place like you would stay in place on Earth. Would that be the same physical effect on your body, you know, in one case as in the other? And I'm not sure it is.
But then you have to find a discrepancy. That's what I've been trying to do.
Yeah. And that's the homework. But that's the homework.
Oh, but you're not doing any of your own homework.
I just give out homework.
Ask the question and say your gut thing. Might be a difference.
Let me tell you how this works. Let me tell you how this works. I'm the guy who gives the homework.
I want to know a great example that separates the two.
I'm the guy who gives the homework. You are the one who's supposed to do it. Okay, so if anyone has a good idea of whether it would be the same.
One question.
Yeah.
If you make the torus, assuming you had the same thing, but it was really huge, so big that you could fly in it.
Would with an airplane.
Anything? Yeah, with an airplane.
Okay, good. Good tube, scenarios. Love them all.
In that tube, would it change the flight of the airplane?
Well, does the fly get pulled inside an airplane?
How would? In fact, let's take the same Stanford torus, and you have a fly flying there.
Yeah, you got to fly.
Would it
right
feel
there, you go.
Gravity. Would it even know what up and down is? I mean, I think air pressure would come with the spin of the torus. So
okay, put something a little heavier, a bumblebee, or put a bird. Let's put a bird. Now it weighs more than a fly. Now maybe it's easier to deal with that, right? And you have the bird. You have an eagle, and it's flying inside the torus. So it's not touching, the walls of the torus. You are, because you're standing on the torus, fine, you walk, you feel 9.8 meters per second square. But here, this guy, he's flying. He's not being pushed against the wall. He doesn't have his feet against the edge of the torus. Does this eagle that's flying there, flapping in the middle of nothing, does it feel the same thing as on Earth? See, on Earth, he's being pulled by ropes. No doubt about it. The eagle has to fly in air against the ropes. He has to fight the ropes every second of the day when he flies. But here, what is he flapping against? He doesn't have to fight the ropes for sure. So now what is he fighting? Can he fly?
If you make the torus wide enough and you shoot upwards, does it get pulled down?
If you would?
If you make the same torus,
yeah,
but you make it much bigger,
okay,
so that there's a lot of overhead space, right?
Okay.
Make it way wider so that
you
can't see the roof.
Oh, okay, so it's very. Okay, so it's a very big torus.
And you shoot with a gun, a pistol, a bullet up. What would happen? There's nothing pulling it down.
Right.
It only had the initial.
The
speed that it was
the inertial mass
down.
The inertial.
But once it cancels that out, it will start floating.
And the question again that I have is, does a person float in space even though it's got this? What happens if you're not standing directly on the floor, against the torus? Here's the torus twirling around this way, and you're standing like this, essentially, right? You're standing against that. And in space, it doesn't matter. You could, for all you know, the torus is spinning like a Ferris wheel and you're standing on it, fine, no problem. We've got that under control. But what if you jump? Now you jump, what happens? The torus keeps going, and as long as you don't jump for too long, like 2 minutes, and stay in the air. But what happens if you float in there? Are you subject to gravity, or is it like the people who go on a rocket, an astronaut? Does he feel gravity when there's no inertia? And I think you've seen that all these astronauts, they're flying inside their their rocket. If the rocket, or the capsule or whatever they're in, right? If it happens to accelerate, they'll all fall to the floor, not due to gravity, but due to inertial mass. The Newton's second law takes over. Now something accelerated, and this guy feels the force, right? But as soon as the rocket goes back to a constant speed, the guy starts floating again. Right? And let's assume that same rocket now goes and turns around in circles, right? And it does so at such a speed that allows the side force to be acceleration to be 9.8 meters per second square. Will you bang against the walls? Will you fall against the walls? Or will you continue floating in space?
I think you'd eventually bang against the wall.
Will the eagle flying inside the torus hit the wall, or will it float in space?
I think it would actually float.
Yeah, but if it's floating in space, listen, because you've got air in there. Air you do have, no doubt about that. And
also air pressure
yeah, right. But no, you may not hold it. Do you have air pressure?
Air without air pressure.
Well, you have an air pressure. Yeah, you have an air pressure. Yeah, you do have some amount.
Unless we got a leak.
You do have air pressure, but remember, air. Why is air surrounding the Earth? Air surrounds the Earth because you have gravity. You have all these ropes connecting to all those oxygen, nitrogen, etc., garbage that we have in the air, all the carbon, whatever we threw up there. They're all being pulled to the center of the Earth by ropes. That's why the air doesn't go away. If we could cut those ropes, God, has his special scissors and goes in there and cuts the ropes, that air would fly away. So the air is there only because of gravity. But now, when you have air inside the torus, it's not gravitational air. Okay, it's artificial air in the sense that you fill this balloon called a torus with air, right? And you can take it to the pressure you want. You can say, okay, we have the same pressure that we have in our atmosphere here on Earth. No problem, okay? But no longer is it gravitational air. In that sense, it's
oh, you're picky with
yeah. And so now you have this eagle, and he's flying in this medium called air, right?
Who brought an eagle to the torus?
You got the eagle flying inside the torus, right? And you got all this air, and it's got the right pressure. But does the eagle see? He doesn't have to fight gravity, because gravity, again, both for the air and for the eagle, is the bunch of ropes pulling to the center of the Earth. He doesn't have that. The eagle doesn't have that situation. Neither does the air.
But he does have to fight the push that the air molecules have towards the outside of the torus. So maybe it has the same effect.
Here, Eric has a question. He says, the eagle is pushed by air. Yeah. Okay. So
one different. I just thought of another scenario for the torus. For sure. If you remove all the air in the torus, and you have a rocket flying, just hovering off the torus, it would eventually float. You would only have to.
Why would it float?
Because
isn't the torus spinning and throwing it against the walls?
No, because
why not?
If you remove the air,
it's what?
There's no air there to transmit this motion towards the outside of the wall.
Even if you had the air. We have the situation where we have no gravitational acceleration. All this is Newton's law, which is inertial mass, okay? We have to consider that constantly when we look at the torus, because we're out in space, we're far away from the Earth, we're far away from matter, from tons of matter. Right now, we got rid of gravitation, gravitational acceleration. Now, all we have is Newton's law. No matter where you look inside the torus, well, unless the case we discussed a minute ago where you are connected to the center of the torus, but there's not enough matter there to cause really gravitational acceleration towards the center of the torus. So all we have really is this artificial Newtonian second law acceleration against the torus. And air is filled in there, because you have to breathe, and you can put it at the pressure you want. You can say it's the same pressure as here on Earth. But now you have this eagle flying in there, and the question is, what happens to the eagle that's flying out there? You're saying, well, he's floating in air. But see, on Earth, he has to fight gravity. That's why he pushes against the air to float. But now he doesn't have to push against the air to float, because he's not fighting gravity. If anything, he would have to hover above your head. And again, you're standing perpendicular to the edge of the torus, and here's the eagle behind you or on top of you, right? Is he fighting Newton's law, or is he fighting the gravitational law? See, if the Earth was over here, he would be fighting against the Earth. But now does he have to fight the acceleration caused by the movement, the rotation of the torus? That's the question.
One good topic on evidence or thing to research about this whole topic is G-force for pilots.
Okay.
G-force?
Yeah, the G-force,
because they deal with this exact topic where, one thing I know is they have these zero gravity rides on airplanes. I'm not exactly sure how they do it. I know it's some direction that of speed where the airplane is either going towards the Earth or away from it, or they do some specific movement at a certain speed so that everyone on the plane starts floating, essentially.
Right, right.
But then, I don't know for sure.
Yeah, they create that gravitational...
What differences...
Yeah, and again, when we toy around with gravity like that, you know, where the airplane just makes a curve, and then during that split second, I don't know how many seconds it lasts, you're floating, you know, you have anti-gravity, and that's one issue. But another issue that you have to take as homework, you know, to think about is the following. You know, on Earth, all the atoms of oxygen, nitrogen, whatever forms our atmosphere is pulled towards the center of the Earth. Fine. That's why we have a given pressure at different levels of air, right? But here you don't have that situation. Here you're creating artificial pressure as well. You're filling a balloon with
constant
with so much air, and first of all, yeah, the air is uniform throughout the torus. But now you don't have you know, the ropes pulling on each atom of air, of oxygen or whatever you have in there, right? You don't have gravity pulling on those. That's not what's keeping it there. What you have is really artificial air, in the sense that all you did was put a bunch of air in there and compressed it to get the right pressure. That's all you did. But the air is not fighting against gravity either. So neither is the air fighting against gravity. The eagle, does that make a difference?
I guess
that's the food for thought.
That's the last question for food for thought.
Yeah.
If you have a chamber, I mean, you can do this on Earth. If you have a chamber full of gas and you spin it faster and faster and faster and faster, does the gas eventually only occupy the outside of that wall?
Because of the rotational motion, because centrifugal force.
Or would it be constantly? Would the air pressure stay the same?
And again, if you do that on Earth, if you do it on Earth, then every atom is still connected to the center of the Earth. The question is, if you do the same thing out in space where there is no gravitational influence, you know, would that be the same? And again, lots of homework. You know, all this stuff is for you to think about, and you know. Come on, let's see what we got. One more question. Oh man, we're getting sophisticated. There's a lot of situations. Well, now you got a million of them, you know, to think about. Air, the eagle. We have the fish in the water.
the
fly in the airplane. The what was the other one you said? The airplane. The G. You know, the artificial gravity that we create. They did it for Hawking and so on. Okay, folks, I guess we'll have to continue tomorrow, but there's a lot to think about. And I'm not saying I've got all the answers, okay, by the way. I've got more questions than answers, and you know, we're trying to think about this, visualize them, how they would function under the rope model. And, you know, if you're just looking at numbers, no problem. You know, then you're a mathematician, you say, hey, you know, we did fine. But when you start looking at the qualitative differences between math and physics, especially under the rope model, then you got a lot to think about, because you got to try to visualize how this works. We'll see you tomorrow. Okay, same time, same station. Bye-bye.